Look at redox reactions and oxidation numbers. Take a look at the pottery. You can see these pretty colors. They are the result of different metal ions in different oxidation states. So we know our transition metals can exist in a bunch of different charge states, oxidation states is what we'll say. Let's take a look at some of the other elements though. We know the noble gases are typically uncharged, right? We're going to say they have an oxidation number of 0. Halogens can be -1 ions, oxygen -2 ions, right? -3, we know this, +1, +2. But you'll notice that there's a lot more possibilities for oxidation numbers. So they're not just -2 ions, but they exist in different oxidation numbers, depending on how many electrons they have around them. So to assign oxidation numbers, which are a really good way for us to recognize if a redox reaction is happening, if electrons are being transferred, oxidation numbers change. So we'll use these to look for those. So there's a couple rules we have to know to assign them. All right, the first one is the oxidation number of an atom in its elemental form is 0. So this is, for example, iron solid would be 0. Hydrogen gas would be 0. Oxygen gas would be 0. Right? These all have oxidation numbers of 0. The oxidation number of a monatomic ion is equal to the ion's charge. That makes sense. So if you have sodium +1, his oxidation number is +1. Chloride, -1. What about O2 minus would be -2. All right. It gets a little trickier, though, in some covalent compounds where you have to figure things out. So for example, well, let's look at this one. So here we have sodium chloride, right? What are the oxidation numbers for each element? Well, we know it's an ionic compound. It's +1, -1, so this would be +1 and -1. It gets trickier, though, if we have something like this, right? Where are the electrons? It's going to be harder for us to say. It's not ionic, it's molecular. So what we're going to learn right now is that hydrogen usually exists as +1. Oxygen usually exists as -2 as a oxidation number. And so from that, we're able to figure out the rest, right? The net charge on this molecule is 0. So what we know is that +1 plus -2 plus whatever Cl is has to equal 0. And so you can see that chloride in this case must be +1. Right, we'll do some more examples of that. But so the rules we're going to use is that hydrogen in a molecule is usually +1. It can be -1 when it's combined with metals. So like, I don't know, calcium hydride, is that real? Wow, bad work by me. How about sodium hydride? That's real. So in this case, this would be +1 and this would be -1. Oxygen is usually -2. There's some cases, though, where it's not. In peroxides, where you have this OO bond, they're -1. And it can also be a superoxide where they're -1/2. Right? But for us, most of the time, it's going to be -2. Halogens are going to be -1, right, if they are ions. But they can be a whole bunch of other different oxidation numbers depending on who they're connected with, right, like we saw here. All right, and the last rule is that the sum of the oxidation numbers of each atom in there has to add up to the net charge on the molecule or ion. So if this is 0, right, then the sum of the oxidation numbers must be 0. And I don't have any with charges. We'll make one up at the end here. All right, so take a look. If O is usually -2, right, the oxidation number for O is -2. Each atom, each element gets an oxidation number. But I need to use this -2 to figure out what C is. If I have 2 -2s, that means whatever C is plus -4 equals 0. So C must be +4. We're going to follow the same rules here. We know that O is usually -2, so this guy's going to contribute -8. K, potassium, as an ion, right, this is an ionic compound, potassium permanganate is +1. So we know that whatever +1, whatever plus Mn plus -8 equals 0. 0 again because there's no net charge, right? There's no charge up in the air like this or something, right? No charge. And so if we add that up, it looks like this guy's going to be +7. Does that make sense? So we're saying K plus Mn plus 4 times O equals 0. +1 plus 7 plus 4 times -2 equals +8 and -8 equals 0. Nice. It's correct. All right, you do this one, MnO2. Right. O is usually -2. Right, 2 times -2 is -4, so Mn must be +4. carbonic acid, O is usually -2, H is usually +1. So 3 times -2 is going to be -6. 2 times +1 is going to be +2 plus 6. And the net plus C equals 0. So C must be +4. Mn is in his elemental form, so it's 0. Finally, what about SO4 2-? So we do the same thing. So here S will have O. O is usually -2. 4 times -2. So whatever S is plus 4 times -2 equals the charge -2. So S minus 8 equals -2. Looks like S must be +6 in this example. All right, so this is how we're going to assign oxidation numbers. Right? There's a couple of rules you have to recognize, and then just practice them. We're going to apply these now to identify if a reaction is a redox reaction or not. And so what you do is you look at the elements on both sides, and then you follow and see what happens to them. So sodium, let's assign oxidation numbers. Sodium here would be 0. He's in his elemental form. Over here, he's in an ionic compound, and his charge as an ion is +1. Chlorine, elemental form, 0. Chloride is an ion. So I'm going from 0 to +1 and 0 to -1. If you go from 0 to +1, you're losing electrons, right? You're becoming more positive. So that is losing electrons is oxidation, right? Losing electrons, oxidation. Oxidation is losing. Here, if I'm becoming more negative, I must be gaining electrons. And so gaining electrons is reduction, or reduction is gaining. Okay, so we can split these. First off, we recognize it's a redox reaction because oxidation numbers change. But we can split them now into their half reactions. So I just separate the oxidation part from the reduction part. We said that sodium is being oxidized, so I write Na solid goes to Na plus. Right, and we don't have to bring coefficients down for this guy, but we do need to make it balance. Chlorine is being reduced to chloride, and so that's the reduction half reaction. So again, we can just double check this, right? So 0 goes to +1, oxidation. 0 goes to -1, reduction. And then finally, the reducing agent is oxidized. So sodium was oxidized. He is the reducing agent. If you are in the oxidizing agent, is reduced. So chlorine is reduced. He is oxidizing the other guy. He's the oxidizing agent. Okay, so we can determine if it's a redox reaction, and then we can identify the two half reactions, the oxidation half reaction, the reduction half reaction, and then the reducing agent and oxidizing agent. The reducing agent is oxidized. The oxidizing agent is reduced. Oxidizing and reducing agents can only ever be reactants, never pick products. All right, good work. Let's see these in the different forms. So we know that we have combination reactions, decomposition reactions, right? Two things becoming one thing is combination. We can practice by assigning our oxidation numbers. So sulfur would be 0. 0 goes to -2 and +4. So what does that mean? It means that sulfur goes positive, loses electrons, it's oxidized. O gains electrons, becomes more negative, it's reduction. That's a redox reaction. In combination, let's take a look at this one. So sodium goes to sodium, H goes to H. Sign oxidation numbers. So here, this is the case where this is hydride. So sodium is +1, H is -1. 0 and 0, and so sodium goes from +1 to 0. That then is reduction. H goes from -1 to 0, right? It loses electrons. That's oxidation. All right, so different examples of decomposition. So we have combination redox, decomposition redox. We can have more examples of this for some reason. Yeah, we just saw these. I don't know why we're looking at them again. Bad work by me. Combustion reaction is a really important one to recognize. So when you react some alkanes or different compounds, alcohols, with oxygen, you get CO2 and water is the common. In a perfect oxidation reaction, you would have two products, carbon dioxide and water. And so that's what's going on here. It is a redox reaction. Let's just check O. O goes from here to here. His oxidation number is oxygen is 0. Here he's -2, right? He actually does it twice, doesn't he? He goes here and he's also -2. But he is being reduced, so he is oxidizing the other guy. And finally, we have a double displacement reaction. So here's sodium reacts to give me sodium +1. That's oxidized. H, here's +1, and it goes to 0. That's reduced. And so this is what happens when you put sodium or lithium metal into water, right? It dissolves with bubbles. That's hydrogen gas forming, right? If you put phenolphthalein in there, you're making hydroxide, right? You're making the pH basic, so it turns pink. And then finally, because this is exothermic, it's exothermic enough typically that the hydrogen gas that collects over here can explode, which is also super fun, right? Let's waste some time and put a little yellow in there and be good. Oh, yeah. All right. Here's another metal displacement reaction. If I put zinc metal in with acid, I get zinc chloride and hydrogen gas again. All right. We'll talk about those half reactions and oxidizing agents a little bit more next time.